Hello. We are going to continue our work with applications of the DeMoirvres theorem by giving another example of finding the roots of a complex function or a complex equation. So this is going to be exactly the same steps, and again it links in strongly with what we would have done for the general solutions of trigonometric equations when we were doing trigonometry. Now, let's dive straight into our method. So I have z to the power, I want to find z if z to the power of 4 is minus 2 plus 2 root 3i. First job is I need to turn z to the power of 4 into polar form. It's in rectangular form or a plus bi form. I need to turn it into polar form so that I can apply the DeMoirvres theorem, and I'm going to get the fourth root, or the power of a quarter of both sides, to find the values of z. And that's going to be my general method. So first of all, draw our picture. Does not need to be pretty. So I have minus 2 on the real, and then plus 2 root 3i on the imaginary. So I'm up somewhere around there. Doesn't need to be perfect. This is the angle that I'm looking for. That's my theta. This is going to be my reference angle if I draw in my model triangle. So I'm going to need to find the modulus, or the radius as it's often called with the DeMoirvres theorem. And I'm not going to need to find my angle using my model triangle. So I'm going to redraw this little model triangle here. And again, model triangle, I am not interested in the direction. I am only interested in the magnitude, the size. So I've gone 2 and then root 3i. I've kept basically the same orientation to make it easier to follow, because trying to rotate these if they were in a funny quadrant would be a problem. Speaking of quadrants, I am in the second one, and on my imaginary and my real axis. So now I'm going to find my modulus, which is also called or. So my radius or my modulus, both the same thing. They're going to be just using Pythagoras. Or squared would be equal to these two sides squared and added together. So or, which you could also write as the modulus if you like, will just be 4, square root of both sides. And I may as well write that in just for completeness. So I now have my modulus of my z to the power of 4. And now I need to find my argument. So my reference angle is where I start off with that. That's my alpha. And I know that tan of alpha is equal to opposite over adjacent, 2 to root 3, inverse tan of both sides, and I get alpha is equal to pi over 3. Again, I'm working in radians. I could work in degrees. Often you'll see the examples in or questions in radians, so I'm giving you examples like that, but you can work in degrees unless they explicitly tell you otherwise. So I have alpha is pi over 3. Now, how am I going to use that to find theta? Well, I know that if I look at my picture, if I rotate around through pi radians, I have gone back by alpha. So I'm back pi over 3, so theta, because I'm in the second quadrant, my angle that I'm looking for, my argument, is equal to pi minus alpha, which is pi over 3. So theta is equal to 2 pi all over 3. So that is my setup done. I have my radius or my modulus, and I now have my argument sorted. So z to the power of 4 is 4 cos of 2 pi all over 3 plus I sine 2 pi all over 3. But I know to get my generals, to get all of my solutions, I must write this in general form. Which means that I acknowledge the fact that if I'm at this point and I rotate around through 360 degrees or 2 pi radians, I would end up at exactly the same point again. If I add 2 pi radians, or 4 pi radians, or 6 pi radians, any number of complete rotations around my circle would bring me back to exactly the same value of z. So they'd all bring me back to the same number. So they're all valid solutions. So the most general version of z to the 4 includes an acknowledgement of that fact, and this is going to help me when I get my fourth root to find all of my different possible solutions. Any number of complete rotations, again, would bring me back to the same point on my circle. Now I have everything written in general form. I can take the fourth root of both sides. In this case, I'm going to write it as a root. You can always write it as a power, but just to show you both methods, we take it to the power of a quarter would be the other way of writing it, but you could theoretically see it like that. And we would end up with, well, the fourth root of z to the power of 4 is just z. So now we have the left-hand side as we want it. We're looking for what z is. I'm going to write this as powers because it's neater for what I'm doing. But we're taking the fourth root, which is power of a quarter. Cos of multiply your power. This is where we're using the DeMoirvres theorem again. We're on page 20 of our log tables using this rule. 2 pi over 3 plus 2 pi n plus I sine of a quarter. Again, you put your power on your radius or your modulus and you multiply that power by your angles. And we are now going to simplify this to make it easier to see what is physically going on as we rotate around. So 4 to the power of a quarter would be the same as root 2. You can write it as 2 to the power of a half if you like, or leave it as, well, actually no, you should simplify it down to 2 to the power of a half or square root of 2. When I multiply this in, I end up with pi all over 6, which I recognize as 30 degrees, plus pi n all over 2, plus I sine pi over 6, plus pi n all over 2. Now, just quickly, before we start subbing in, physically, what can we see is going to happen here? Well, we're going to start off when n is 0, with none of our extra rotations. We're going to get cos of 30 degrees, or cos of pi over 6, and sine of pi over 6, whatever that works out to. Then every time we increase n by 1, we're going to be adding on pi over 2, so 90 degrees. So we're going to rotate, we're going to start off at 30 degrees, and we're going to rotate around our circle through 90 degrees each time. So how many solutions am I going to get before I start repeating solutions? I'm going to have to rotate around 4 times before I start repeating solutions. So I'm going to end up with 4 valid solutions, 4 unique solutions. And that makes sense because I have a fourth power here, so I'm expecting to get 4 roots of a quartic equation. So let's start subbing in values for n. I know that n starts at 0, just like when we were doing our general solutions to trig equations. And I just start subbing in values for n. This is all just substitution and calculator work now. Write this out. Cos of pi over 6 plus 0 plus I sine pi over 6 plus 0. And we end up with root 2 on root 3 over 2 plus half I, which ends up, depending on how you approach simplifying it, as the square root of 3 over 2 plus 1 all over root 2I. Then we start subbing in n is 1, n is 2, n is 3, and after n is 3, we should start to find that we are repeating solutions. But I'm going to write that in and come back to you. Now, when I have done my substitutions of n is 0, n is 1, n is 2, n is 3, this is an extra. You do not have to write this. If you do write it, you won't lose marks or anything, but I'm just putting it in to highlight what is going to happen after we get to n is 3. We end up back where we had for our first solution when n is 0, because we have gone through a complete rotation. If I look at what happens on my n is 4 situation, I have pi times 4 all over 2. Simplify that, that's 2 pi. I'm adding on 2 pi to my original angle of pi over 6. That effectively is the same as just cos of pi over 6 or sine of pi over 6, because I'm just going all the way around back to where I started. And if I draw that as a quick sketch, what does all of this look like? Well, I start out here. This is one of my values of z. This is going to be where I'm going up by pi over 6. This is my angle pi over 6, going up by 30 degrees. And what do I do each time? Well, I can see that I am going around by pi over 2 each time, which is a quarter of a circle, or 90 degrees. Pi over 2 would be 90 degrees. Pi is 180 degrees, so pi over 2 is 90 degrees. So my second solution is at 90 degrees to my first one. Brings me up to here. So I've gone through 90 degrees there. I go through 90 degrees again. Through 90 degrees again, I get my second solution. Sorry, this is my first solution here, my second solution here, my third solution down here. I can see that I have a minus real and a minus imaginary, so I'm down here. And then I again rotate through 90 degrees. Through 90 degrees, and I end up down here on the plus real and minus imaginary. Plus real and minus imaginary. And then what happens if I make n4? Well, I just rotate around another 90 degrees, and I would end up back where I started on this number again. So any increase in n after this is just going to keep hitting the same numbers over and over again. And that's how our solutions work. That's why we only end up with a particular number of solutions, because when we get the fourth root or the fifth root or the third root or the square root, we are breaking up our complete rotations into half rotations or quarter rotations or third rotations. And that's how many solutions we are going to end up with before we start to repeat ourselves. And that is what we need